everyone, this is Mohammad Sadiq from School of Physics in association with Fathom Academy for iit-jee and NEET. Today I will talk about physics and mathematics. This is a very important and special segment. We are going to start the discussion of basic maths, which is required for doing physics at our level. Now in this segment I will take the liberty of speaking mostly in English. I will switch back to Hindi as I begin the formal discussion of basic mathematics. Now physics and mathematics. Now what is the obvious question is, why maths? Why it is important to have some basic understanding of mathematics while dealing with physics? Well, it can be a difficult question. If simply put, it is the only language which physics and the laws of nature can be expressed efficiently in. And if more simply put, we can say that mathematics is simply inescapable. It is inevitable. You cannot do anything about it. You cannot run away from mathematics, and perhaps it is the language spoken by the nature itself. The fundamental laws of nature are mostly simple in character, but their application in different situations becomes quite difficult, and we need mathematics there to help us. Interestingly, the fundamental laws are themselves mathematical. For example, we know this law, this is a very basic law regarding motion of objects and particles. F is equal to ma. Here F is force, mass is m is mass of the particle, and a is acceleration, which is change in velocity per unit time. It looks simple and of course mathematical. Let us try to say the same in some other ways. Let us try to avoid mathematical statement. We can say that force is the product of mass and acceleration, which still seems mathematical. We can say in another way that if mass is increased, more force will be required to have same acceleration. Or we can also say that if force is doubled and acceleration is halved, if mass is doubled and acceleration is halved, we need the same force there. Now these all may seem physical in character, but they are all exactly the same as F is equal to ma. In whatever language we try to say the same thing, we will ultimately come to this statement. You cannot escape it. If it is mathematical, it has to be expressed in mathematical form. Now many other things can be readily followed from this expression. If F is equal to ma, then I can write acceleration as F over m. Then from here I can say, I can very easily conclude that the directions of acceleration and the acceleration and force will always be same, as mass is always positive. And one important point that I can deduce from here, if force is 0, then acceleration is also 0. And from the definition of acceleration, if it is 0, then velocity is going to be constant. The velocity vector is constant. Now I can deduce, I can make a point that if you have to bring any change to the velocity, you need force there. If there is no force, the velocity vector is going to be constant once and for all. Now when a law is right, it can be used to find another one. The more laws we find, the deeper we penetrate nature, and mathematics helps there to see the tapestry and eventually helps connect the dots and uncover the mysteries. For example, F is equal to ma. This is not an ordinary mathematical statement. You are looking at a big picture with all its patterns to have some better sense of appreciation. So if the laws of nature are mathematical, they have to be expressed in mathematical form. It is impossible to explain honestly the beauties of the laws of nature in a way that people can feel without their having some deep understanding of mathematics. Like a mother loves her children, it is beautiful, it can be felt and admired without any quantification and association of numbers. In case of natural laws, there may be an underlying harmony and beauty that is non-mathematical in character and so far have only been known to nature and not to us. But still, mathematical form of natural laws are beautiful if we can appreciate the fact that mostly simple laws are there at the bottom to govern the tremendously chaotic behavior of our universe. Having said so, now let us focus on the relationship between physics and mathematics. The mathematical symbols in an equation can convey information at much greater speed and allows the possibility of manipulations at the same time. For example, there is this law of gravitation, the gravitational force between two particles g m1 m2 over r square, where m1 m2 are the masses of the two particles exerting force on each other, and r is the distance between them, g is some constant. Now I can say that if you reduce the distance to half, if you make r by 2 and keep the masses same, then force is going to be 4 times. This mathematical statement can have a translation like this. We can also say that if we keep the distance same and change the masses to half, we can, if we reduce the masses to half, making m by 2 and m2 by 2 and keeping r same, then you can say that force will be reduced to F over 4. It will become 1/4 of its original value. So for this mathematical statement, we can have these kinds of translations. It can have translations like this, which at times may appear confusing if we do not express the law in this form, but we are trying to say the same thing through these statements. They may seem confusing and disconnected from one another. But in mathematical form, it is one thing, just this beautiful statement. And for this, you have to have some understanding, some basic understanding to understand this, to appreciate its beauty, and also to be able to manipulate this law at your ease. Mathematics is not just a language, it is a language plus reasoning. It allows us to go deeper in reasoning without ever losing the sight of what is being discussed. Now let us look briefly into the discovery of law of gravitation by Newton to understand this relationship between physics and mathematics better. It was the Italian physicist Galileo who recognized the fact that all bodies, irrespective of their masses, accelerate towards Earth with a constant acceleration. He did experiments with bodies rolling on inclined planes and arrived at a value of acceleration due to gravity which was close to the more accurate value obtained later. Namely, we know that the gravitational acceleration is 9.8 meter per second square. Newton, on the other hand, was interested in a phenomenon that seemed unrelated to the idea of Galileo. He calculated acceleration of moon around Earth by assuming, this is important, by assuming that Earth is pulling the moon. So moon is going round the Earth due to the pull by the Earth. Now from the ideas of circular motion proposed earlier by Newton, if an object moves in a circle, then the acceleration is v square over r, and this acceleration is towards the center. Here v is the speed of the object and r is the radius of the circle in which the particle is moving. In case of moon, this radius of the circle is the distance of the moon from the center of Earth. So in case of moon, the acceleration can be written as speed square of the speed of the moon divided by the distance of moon from the center of Earth. And this distance was known at that time to be 3.84 into 10 raised to the power 8 meter. And this velocity, from the basic definition of velocity, that is distance upon time, we can write distance as, in one revolution the total distance covered is 2 pi rm divided by time, the time for one revolution. Let's write this capital T. We also call this time period. Now the time period at that moment, or the time period, as we know, time period for moon to go in one round around the earth is 23.7 days. Now if you put this in this formula, we come at am is equal to v square, then it becomes 4 pi square rm. Here we pull, here it is rm square, and there is one rm in the denominator, so just one rm will be left in the numerator. So divided by this t square. Now put the values, 4 and 9.86 for pi square, and then rm, which is 3.84 into 10 raised to the power 8 divided by t. Now you have to put this t in seconds. So 23.7 days and 24 hours in a day and 60 minutes in an hour and 60 seconds in a second, and then make whole square of all these. Then this value comes out to be 0.027 meter per second square. Now this is very small in comparison to the gravitational acceleration on the surface of earth. So this value obtained from the Newton's argument is much smaller than the gravitational acceleration we find on the surface of earth. So Newton reasoned that force of gravity decreases with the distance. It is greater on the surface of earth, and as we move away from the center or the surface of earth, the force of gravity decreases, and he assumed that this force decreases in proportion to the inverse square of the distance from the center of earth. So we can say that this acceleration is inversely proportional to the square of the distance from the center of earth. Then gravitational on the surface of earth will be 1 over re square, where re is the distance from the center of earth on the surface, or that is radius of the earth. And let's divide these two. Then we have am over g is equal to re square over rm square. Now put the values. This is am is 0.027 divided by g. This is equal to re. Radius of earth is 6.4 into 10 raised to the power 6 divided by rm, which is 3.84 into 10 raised to the power of 8, and make whole square of, and then g is equal to, if you calculate this, g comes out to be 9.7982 meter per second square, which is close to 9.8 meter per second square, the value we obtain on the surface of earth. So he was right in his reasoning, and then he went on to propose the idea that force due to which everything falls on earth is same that causes the moon to go round the earth, and this force is in proportion to the square to the inverse square of the distance. And also, now this is important, he reasoned and proposed that the law governing this force is applicable everywhere in the universe. Later on, his law of gravitation was tested and was found to be correct. Now again I say, when a law is correct, it can be used to find another one. Eventually, many other things were discovered after the discovery of gravitation. By looking at the moon of the Jupiter, the speed of light was calculated for the very first time. When this law was applied to the motion of planets like Jupiter and Saturn and Uranus, the Jupiter and Saturn went according to the calculations, but Uranus was off the mark. A proposition was made that the unusual motion of Uranus was due to a planet which was unseen until then. They asked the observatories to turn their telescopes and look there in the sky to find a new planet, and thus was Neptune found. So Neptune was originally discovered on paper using pens and pencils, helped by none other than the mathematics. Now, these brief turn of events from Galileo to the discovery of Neptune present us a picture looking at which we can have an idea about the relationship between physics and mathematics. Let us look on the same relationship from a different perspective. The mechanism of sound propagation somewhat resembles the relationship between physics and mathematics. We know that for sound to propagate, a medium, be it liquid, solid or gas, is required. The medium has its own independent existence. It does not depend on sound, but few of the properties of the medium are used by sound for propagation. Sound in itself is a physical quantity. It uses the medium just as a carrier. Same way, physics is the understanding of behavior of nature. But for this understanding to float smoothly, we need the facilities of mathematics. There is a lighter note on the relationship between physics and mathematics. If you ask a mathematician to give you some maths about the three-dimensional space, he would say, why just 3 dimensions? Take maths from us for n dimensions. Then you would say, no, we just have only 3 spatial dimensions. Then I would say, okay, well, just put n is equal to 3 there. Okay. Now, let us take another example for understanding this relationship. There is the motion of simple pendulum. If you suspend a small object using a thread or a string and displace it, this position is called the mean position of this bob. If you displace this bob from its mean position, the bob will oscillate about its mean position. So if you displace it here and release it, it will oscillate about this mean position. It will go forward and backward, to and fro motion it will perform. Now, if you take continuous snaps of the bob at different positions to locate it, and then plot those positions against time on a graph, then the graph comes out to be like this. It is like this. Initially the displacement is maximum and then it decreases, it becomes 0, and then it increases on the other side and then again it becomes 0, and then so on. Now you would think how to describe this position. Let us take this as the position, and on this axis we have time. Now you would think how to describe this relationship between position and mathematics. Well, tell your mathematician friend and he would promptly give you the function y is equal to cos x, where use y for displacement and x for time, and the problem is solved. This is the function which can perfectly govern the motion of the simple pendulum. Now you are ready to do manipulations. If you can write this x in terms of t as x is equal to cos t, then you can do many manipulations. If you differentiate it, you can have the velocity. If you differentiate it further, you will have accelerations. So you are ready to manipulate this and find many other things and rules. So once again, mathematical symbols in the equation are conveying information at much greater speed. If you are not using this statement and trying to say the same, then it becomes quite complicated, and the same thing is conveyed in a longer period of time. Let us take one more example to understand this relationship. When a charged particle moves in a magnetic field, it experiences a force which is in direct proportion to the amount of charge, its speed, and the strength of magnetic field there. And additionally, this force on the moving charged particle is always perpendicular to its velocity vector and the magnetic field vector. Now all these can be written in a crisp way as, if the force have such behavior, then it can be written in vector form as F is equal to QV cross B. Now, if you write the force in this vector form and we know some vector mathematics, then we can say, then we can very easily infer that whenever the velocity vector and the magnetic field vector are parallel or anti-parallel, this force on the charged particle is going to be 0. Now, we may have missed this point at the first point in the observation, but when we write the same observation in this form, it is very easy to infer that whenever the velocity vector and the magnetic field vectors are parallel or anti-parallel, the force is going to be 0 on the moving charged particle. Now, I hope that I have convinced you that mathematics is important for studying physics. Now, we can proceed with our discussion of basic maths. We will use maths as a tool here. How that tool is made will be beyond our discussion. The tools will be used to give concrete shape to basic ideas and propositions. It will also be used for manipulating a given law or rule to find another law or rule. And it will be used to apply the laws in various situations and bring around explanations and answers to the problems. We can sum up how we would do maths with physics in 3 steps. Step 1. There will be a qualitative statement describing some physical situations. Step 2. We will translate the qualitative statement into mathematical form and solve it to arrive at a result. Step 3. We will then again translate back the mathematical result into qualitative statements and interpret the results physically. One more thing we should keep in our mind, we must keep in our mind. Now, this is very important for the students, that physics and mathematics are not distinct. We must keep in our mind that doing physics without mathematics is very, very difficult. So, if you have any fear regarding mathematics, just let it go and learn mathematics. Well, how much mathematics to be learned? It depends on the level of physics that you are doing. In our course, the forthcoming discussions will suffice. All the best. We will meet very soon with the discussions of basic mathematics. Thank you very much for being with me.